Okay, guys, good evening. Am I audible to you? And I am visible to you also?
Good evening.
Yeah, I am visible to you, audible to you also. Please respond. Hello. Okay, I am starting. So, actually, tell me. Uh, uh, Mr. Patil, tell me this person. Okay. Patil, tell your concern. Yes, Patil. Please text your message or any concern you have. Please text. I'll address it. Okay, so I think there is no issue in my voice and audibility and also the visibility. So I'll start this session. So thanks for this evening for joining this evening. And actually, I mailed the NPTEL guys regarding the week 5 assignments and their questions regarding the question, and it is not in accordance with the lectures as provided regarding the based on week 5 lecture. It is there is no relevance of the question relation between the questions and lectures lecture note. I think they have heard our voice, and I think they have extended your submission deadline for week 5. So actually, in week 5, it was based on American Concrete Institute method, and they are asked to solve the using that formulae and also that methodology, and we have already done that. So I think no need to, and that video is shared in week 6 lecture. So it is just a they are not updated that part in the week 5. So it was bit difficult for us to solve the questions, so that I mentioned in the mail. So it's fortunate that they address this issue. So today's lecture, actually I want to cover some few points regarding the today's lecture, which mm, first I will cover up the assignments, then I will go to the this content we lecture note, and I will discuss a few points, the important points. Then we'll, as promised, we'll be discussing the MCQ type questions. The first question is, I think I'll share my screen. Yes. Okay, so I think it is getting shared and there is no issue in the regarding the visibility. So the first question is the minimum grade of concrete required for the structure susceptible for severe exposure condition according to the IS code. So it is about the concrete RC mixed RC design. So it is yes. Yes. So the first question is the minimum grade of concrete for severe condition. So according to that table, this in the IS code is already mentioned mild, moderate, severe, very severe, extreme, and I also write down the table's content, and you will easily get understand what will be the probable answer to the question. So first question is. Okay. Yes, first question is a minimum grade of concrete. Minimum grade of concrete at severe, right? A severe exposure condition. Severe exposure, condition. So there are many exposure condition. Based on that, we will be deciding in what is the actually in the IS code. It is bit different from the ACI method, because in ACI water cement ratio in mainly dependent on the MSA, that is the maximum size of aggregate, and also and the strength, yes, strength criteria. Okay. Yes, water cement ratio is, sorry, not the not a maximum aggregate size of aggregate. It is mainly based on the strength criteria. However, in the Indian code scenario, it is mainly based on the experience. Okay, so and if there is no such experience mentioned, so IS code has provided the water cement ratio, minimum water cement ratio, maximum cement content based on the severe. It's based on the exposure condition. So you have to be careful while designing both two methods, because IS code mainly focused on the experience, and you have to regard that. You have to go with accordingly. So mild. So this is already in IS code 50 is already available. IS code 50, still I am writing 2000. So exposure condition, exposure. So mild, moderate, moderate, severe, 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 very severe, extreme, extreme. So accordingly is minimum minimum cement content in kg per meter cube, or kg per meter cube. Okay, kg per meter cube. Okay, maximum water cement ratio, minimum grade of concrete, minimum grade of concrete. Actually there is two things. One is plain concrete, one is reinforced concrete. Okay, so I think this what we are doing is all with reinforced concrete. There is no plain concrete situation, and if there is plain concrete, you can easily identify the chart. Okay, it is not a big deal. So so mind exposure condition, um, in mind. Okay, so okay, simultaneously I'll write these two things. Okay, so for the plain concrete, so it is the plain concrete, right? Plain concrete, uh, I am in shorthand, I'll just write is P is reinforcement, P reinforcement, P reinforcement, mean plain concrete, R for reinforced concrete. Okay, so in mild is 220 minimum, 220 for plain it is 220 kg per meter cube. For reinforcement it is 300, little more. For moderate it is 240, moderate 240, 300 the minimum. Severe it is 250, 250, and minimum is 320, 320, 260. For very severe condition it is 260, and minimum grade of concrete, minimum cement content for reinforced concrete is 340. So you can see for the reinforced concrete, the cement content is much higher than plain concrete. So in extreme 280, 360. So these are the, so and the maximum water cement ratio for mild condition 0.6, 0.6. Here it is 0.55, 0.6, this is 0.5, 0.5 here, and 0.45 here, 0.45, and 0.45. Is 0.4, 0.4. So in very severe, in severe extreme condition, there no change in water cement ratio, the same, both are same. Okay, yes, fine, 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 fine. Okay, 263, 40, 283, 60. Okay, fine. A minimum grade of concrete, what it is? Minimum grade of, for there is no mention of mild. In mild there is, in plain concrete there is no such thing mentioned. Okay, so However, in the reinforced concrete, it is M20. M20. So see, M20. I am repeatedly telling that M means for cube strength. This is not a cylindrical strength. In our Indian scenario, M for that grade. The grade that denotes the cube strength. If it is cylindrical strength, you have to find out. You have to multiply with 0.8 because cylindrical strength is 80% of the cube strength. Okay, so M15 is M15, M25. Okay, M20. So you are seeing that for a particular exposure condition, whenever there is any reinforcement, the grade should is recommended high. So this is a general conception. When there is reinforcement, that grade will be high. So you should not miss that. 30, M20, M35, M25, sorry, M25 or M40. Okay. So these are the charts. So here it is saying that for severe susceptible. Okay, what is the? Okay, I'm just checking. 25, 30, 35, 40, M14, 20, 20, 25. Okay, so severe condition, minimum grade of concrete. Okay, so for minimum grade of concrete, it is yes severe condition. Okay, severe condition. So it is for M20 for plain concrete, M30 for reinforced concrete. I think M20, M30 both are there. So we have to decide what it should be. So M30 for reinforced concrete, M20 for M20 for plain concrete. Okay, plain concrete. So whenever you answer, you just pick one and you can say that this is the case. So there is a lot of ambiguity in the question. And next question is what is the target mean strength of the F25 grid concrete? So I can erase the question or let it. Okay. Target mean strength. Okay, target strength is the mean strength. Mean strength is FCK plus 1.65, 65% variation either here and there, and it's sigma. So it is nothing but M25 is very easy to calculate. To calculate M25 plus standard deviation is 5. So what it is it? 25 plus 1.65 into 5, 33.25. 33.25 megapascal. Okay, so it is the target strength of this concrete. Target mean strength of the M25 concrete. Okay. So now third question. So I think yes. So third question is you are to design the 30%. Yes, this third question have a lot of ambiguity the question, because sometimes they are saying the same MSA and same zone, and they are also adding some fly ash content, and they haven't mentioned the concrete that maximum size of aggregate or the workability. So we have to take the previous example, or the previous example we have to take, because as there is no mention of such information. And also there is a zone is mentioned. Actually zone in our previous assignment, there is no such zone mentioned, because it is based on, because they are asked to solve the question based on ACI method. In ACI method, American Concrete Institute method, there is that there is no zone, that water cement ratio whatever we are getting, or concrete fine aggregate or coarse aggregate, and the volume fraction we are getting based on maximum size of aggregate. So there is no zone effect. So the- if it is zone, then it comes to IS method. So first we will try with the IS method, then we'll explore the option of solving it through ACI method. So that way I plan. So actually in the beginning I want to tell that we have to calculate this. We have to calculate first the fly ash content and the new cement content. Okay. So fly this 30%. So first of all, what are the inputs we have? So inputs we have is 30% fly ash. Fly ash. I think I have to delete this. Excuse me. So fly ash content is 30%, right? Fly ash content is 30%. Okay, so it is 28 days mean strength. Actually, if you if you they already mentioned the target mean strength. Actually, there is, if you use the IS method, there is no such use of use with this target mean strength, because there is nothing to do with target mean strength. Already they have provided all the information. However, if it is in a ACI method, then there is some utilization of this target mean strength. Otherwise, in the IS method, I don't have any relevance of giving the this target mean strength. Okay. Okay. Anyway, we have to proceed. And what is this? This here, fly ash content is there. Target mean 28 days target mean strength. 28 days target mean strength is 35 MPa, right? 35 MPa. And now the water content. Actually, all the contents are given in control. Actually, in the control condition, when there is no such fly ash or a water reducing agent is not mixed. So it is a controlled condition. So in controlled situation, what are the contents in mixed design? Okay. So the content and the cement content, right? The C. So I'll write a C. So okay, I find I better I do is this one, two, is target mean strength. Target mean strength 35 MPa. Okay, cement content C. I just write C. 378, right? 378, 378, 378 kg per meter cube. 4, what it is? Cement. Water content, right? Water content is W. Water content is 200 kg per meter cube. 5. Fine aggregate content. Fine aggregate content is yes. Fine aggregate content is fine aggregate 678 kg per meter cube. And coarse aggregate content is 1155. Actually, when you use the fly ash, so fly ash will just say it's a complementary material, and it will just replace the cement. So after the calculation, you will see there is some reduction in cement content, and also the reduction of coarse aggregate and fine aggregate due to the fly ash content before. Okay, so let's see what are the points, actions points, or what are the calculations. So this is a control mix. Okay, so these are the control mix. Now, first of all, that fly ash content, and actually in IS method, most of the actually few points are there that is not required for solving in a while in using the IS method. Okay, but however in the ACM method, maximum points are relevant. So I'll try to address those things. So first the thing is, whenever there is a no fly ash content, just we have to design the fly ash content, and also we have to find out the new cement content based on the given fly ash proportion. The two formulas are available. One is the two formulas is there. Formula is there. One is fly ash by this is C dash plus a sorry fly ash content plus C dash means new cement content. So actually it is 30% of 0.3. So in C plus F it is actually whenever we add some fly ash in the cement in the concrete system, it actually gets it promotes larger volume, so larger mass. So it is 10% increased, so it is 1.1 C. 1.1 C. So 1.1 C, what is C? What is 378? What? How much it is? 378 into 1.1. 4 415.8 kg per meter cube. Okay, you have to write all along the units, so don't miss the unit. It will be a discredit for you. So fly ash content, what will be the fly ash content? So 0.3 into 415.8 kg per meter cube. So 0.3 124.74 kg per meter cube. Okay, now C dash means the new cement content, what it is? 415.8 minus 124.74 this kg per meter cube, and 415.8 minus 124.74, 291.06 kg per meter cube. Okay, so here is the new, and this is the new cement content. Okay, new cement content. Now this is water content. The first cement content is there. Now we will go for water content. What is the water content? Actually yes, actually there is actually in the highest code mentioned the water content based on the maximum size of coarse aggregate, maximum size of aggregate. So considering the actually the in Indian scenario, MSA is either 20 or 10. So we'll be here we'll be going with the MSA 20 mm and slump 80 mm as previous. Okay, and zone 3, the same zone they are saying. So zone 3, if you have seen the Professor Bhattacharya class, it is zone 3 they mentioned. Okay, so okay, then Then I'll do I proceed further. So what is the first is we got the fly ash content and also the new cement content. Now the water content already there for control mix. What it is, W is 200, so 200 is there. And actually it is a slump is 80. Okay, so uh, actually in the previous section I think you have checked for 20 to 20 20 to 50 millimeter slump. The okay, the thing is already I think there. Yes, I have to tell this thing. Chart is there actually. Yes, got. Actually, I prepared the chart and they're already there, but for my sake of understanding or for you guys to tell, I prepared the chart and tell. Yes, this is the thing is for a rounded aggregate. Okay, rounded aggregate. This the thing is the 40-point slump for is 20 to 25%. Actually, sorry, 25 to 50 millimeter slump. There is a additional requirement of water if for each 50 millimeter slump, additional 50 millimeter slump, the water requirement is 0.3%, 3% water requirement. So I'll just in short I'll mention the table so for your understanding. Rounded aggregate. Okay. For rounded aggregate for 20 to 15 millimeter slump. Yes. Actually, in the ACI method, they are categorized the slump, and based on the maximum size of aggregate, you can calculate, you can find out the or interpolate the water content. However, in the this Indian scenario or IS method, okay, so we have to optimize or we have to find out the this water content by trial. So based on the experience actually, and there's some formulas that are from hand rule is there. So what it is, 20 to 25 to 550 millimeters slump. So this table is valid. So for each additional, each delta is equal to plus 50. Sorry, 50 mm. Del W is plus 3%. Okay. Now for subangular, okay, this is for this gravel. For subangular angular uh, gravel, crushed gravel, subangular gravel plus crushed gravel, and yes, for it is unrounded area, rounded. Okay, aggregate is about minus 10. It is directly it is deducting minus 20 minus 25. So it is subangular, it is crust, and this is rounded. I think rounded means this. I check this information. This both are rounded, so I have to check the information in later class. I will confirm this. What are the things? Actually, it should not be rounded, or here either it will be angular. Okay, so I have to check this. However, these are the charts, and you can follow this one. And for admixture, it is for plasticizer and super plasticizer. So water reduction for plasticizer is 5 to 10%. For super plasticizer, 10 to 30%. And we basically take the 25% for super plasticizer. So these are the charts, and we can follow this. So actually, these all are based on the this 25 to 50. So for the rounded aggregate, this value is based on this 25 to 50 millimeter slump slow. So we have that 80 millimeter slump, so we can do the average thing. So it is about 25 millimeter. The average is 25 millimeter. So 25 millimeter, so it is about it is so one it is 150, it is 50 more. So it can be taken that for consideration 200 minus 0 0.0 0 point more slump is there, so we have to add the water content. So what w dash plus w dash is there 0 0.03 into 200. It is nothing but 200 into 1.03, right? It is coming around yes, it's coming around 206, I think. 206, 200 into 1.03 is 206. Okay, 206 kg per meter cube. 206 kg per meter cube. Okay, now another is due to the addition of fly ash. Okay, due to addition of fly ash, they also mentioned that yes, due to addition of fly ash, due to fly ash, water content is reduced by this 15 water reduction. So del w is minus 15 kg per meter cube. Okay, so water reduction is, so w double dash is 20, 6 minus 15, it is coming around to 191, right? Yes, 191 kg per meter cube. This is the water content. Okay, and now we have the water, we have the fly ash, we have the cement. Now we can go for fine aggregate content. Okay, so fine aggregate content can be obtained from the this conservation of volume, that is very much relevant for IES method. Meanwhile, I have to take your attendance. So this is the yes where I am. This is the yes, conservation of volume. So conservation of volume says that this is, if you its total volume is 1, so 1 is this is the water contour, water plus cement material. Here it is cement, not w double dash, but there is corrected or modified water content. This is a modified cement content, c dash, into specific gravity of cement plus fly ash content is there. Actually, in this conservation, there is no mention of their air content. So air content are not included in this equation. So this is the cement content plus this fly ash content. This fly ash, when fly ash is specific gravity of fly ash plus fine aggregate. So actually in zone 3, it is zone 3, right? So zone 3 it is about 0.64. I will tell you yes, based on the maximum size of aggregate, what is the zone. So zone maximum size of aggregate, so it is 10, 20, 40. Okay, same. And it is zone 4. It is zone 4 very fine. Zone 3, zone 2, zone 1, and point 0.5. Actually these are all the volume. This is the volume for coarse aggregate by volume, coarse aggregate volume by total aggregate volume, total aggregate volume, aggregate volume. Okay, total aggregate volume. So 0.5, 0.66, 0.75, 0.48, 0.48, 0.64, 0.73, 0.46, 0.62, 0.79. So 0.44, 0.44, 0.6, 0.69. So we are concerned with this value because our MSA is 20 millimeter and it is zone 3, so it is this. Okay, so 0.64. So this is the 0.64. So if the fine aggregate, then 1 minus 0.64. So actually this would be, sorry, 1 minus 0.64 into fine aggregate. Actually this section is the water, this is water, this is cement volume, this is fine fly ash volume. So this section denotes the total aggregate volume. So total aggregate volume based on this volume fraction. So if I divide it by 1 by that volume fraction, it will give the total volume of the cement. Okay, total volume of the aggregate. So here we get the finding, we are interested to find out the fine aggregate content. So here it is 1 minus 0.64 fine aggregate, fine aggregate by specific gravity of fine aggregate, specific gravity of fine aggregate by total 1000. Okay, so these are the formula. So fine aggregate content, so I am writing this thing. So W is there. W, what is that? New W was 191. Okay, and this new cement content, what is the new cement content? uh, yes, what is the new cement content is 291.06. Now it is 3.15. Specific gravity of cement is 3.15 plus fine aggregate fly ash content is 124.74 kg per meter cube, and it's 2.2. It is the specific gravity of fly ash plus 1 by 0.36 is fine aggregate. What is the fine aggregate? Fine aggregate, we have to find out the fine aggregate content, and specific gravity of fine aggregate is 2.7, right? 2.7. So 2.7 is this. Okay, so if you calculate, so it will come like this. Fine aggregate is yes, actually 641, 4228, really 4 kg per meter cube. Okay, so if you calculate, I am now I again calculate, I calculate a few hours back, so it should be, I have to calculate again. So 1 minus 191 by 100 thousand minus 291.06 by 3.3150. Okay, by 3150. Okay, minus 124.74 by 2200, 200. Okay, yes, now I can I can multiply this 0.36 to 2.7 to yes 641.4 641.4 fly ash content. And if I want to calculate this coarse aggregate content, the same formula is there: 191 plus 291.06 3.15 plus 124.74 2.2 by 0.64 coarse aggregate. So coarse aggregate is the specific gravity of coarse aggregate is 0.2.6. Okay, actually the table you understand, this is for only for the coarse aggregate, okay, not a fine aggregate. Fine aggregate, so it is all the coarse aggregate content. So coarse aggregate is the volume, all the volume fraction, volume of the coarse aggregate by total volume, total aggregate volume. This is the volume fraction. So similarly we will get this coarse aggregate content is 1098.07 kg per meter cube. You have seen this two value, this fine aggregate value, coarse aggregate value, and the cement content value. These all are reduced because of the fly ash content. This fly ash, when fly ash is adding, it is replacing some coarse aggregate, fine aggregate, and also some cement. And I mean basically this is the replacement. This is the added the fly ash is added to replace the some part of the cement. So cement content are reduced. So this is the new fine aggregate coarse aggregate content. So as you can check here, so actually this you can also do another in another way, or you can find out this yes actually mm, actually this is the total, right? And this is the this and this cement content is there, water content is there, fine aggregate, coarse aggregate content is there. Okay, so you just have to add up these things. So what if you add this all the components, so 378 plus 200 plus 678 plus 1155, so it is it is around total. If we do it total, so it is 2411, it is coming 2411 by meter cube. So it is kg per meter cube is bulk density. Now they are saying that due to the fly ash, addition of fly ash, the and reduction of water, the bulk density is reduced by is 40 kg per meter cube. Okay, reduction in weight density, weight density or bulk density, and weight density is reduced. Yes, reduction in weight density is by reduction. How much it is? 40 kg per meter cube. 40 kg per meter cube is 40 kg per meter cube. It is coming like 49, so it is around 2731 kg per meter cube. And you can both check it with this if it is coming closer or not. So we have this cement content, this is the cement content we have, this is the water content we have, this is the fly ash content, because fly ash is added here, so fly ash should be included in the calculation. So fly ash content here. Okay, so these are the things. So this fine aggregate content, this coarse aggregate content. Okay, so fine fly ash content 124.74 plus cement content 291.06 291.06 yes 124.7 for 291.06. This 124.7 is fly ash content, 291.06 is the new cement content. Water content how much? 191. Now now the fly ash content is 641.4 plus, so the coarse aggregate fine aggregate content is 641.4, coarse aggregate content 1098.07. so it is around 2346. It is around it is coming around, if you add, so it is, if you sum up, so it is coming around 234627. So it is closest to this value 2371. So it is basically it is right. Actually the information is not that compact, so we have to justify our calculation whether it is correct or not, because I think this 40 kg per meter cube is not right. There is some more considering this. Actually this is the correct method to doing the all the calculation of the components based on the IS method. If you consider the IS method, this is the correct way of calculation, because the Professor Bhattacharya also stressed on this formula and conservation of value. So actually the control mix, from the control mix it is 40 kg per meter cube is reduced. However, in our according to our calculation, the reduction is 2411 minus 2346.27. Reduction is 64. So actually it is 65. For our case, 65 reduction is taking place. So in this we have to make it sure that whether these calculations, whether these values are proper or not. Okay, I think for your calculation purpose it will be a big deal. They'll give you the sufficient time and the relevant information, or the credible required information for a problem to solve. Okay, now if I do it by ACI method. Okay, now I'll do it by ACI method. So how it would be? You remember? So mm, yes. Mm. What is happening? Yes. Okay. So if we do it by ACI method, then first of all we have to calculate the water content. So water content is there. Mm, yes. Uh, so water content is we have to calculate this water content based on the uh, yes, yes, uh, for the ACI method. So ACI, if we follow the ACI method, because they have not mentioned the which method you can follow, so we can follow any method. So in ACI method, the mixing water content is based on the slump. The slump is for the 80 mm, and maximum size of aggregate is the 20. So 20. So based on this two information, or water content is should be 200. However, in yes, 200 is water content is already there. So so it is right. It is following the ACI table. So based on the ACI table, based on the table, we get water content, mixing water content, is 200 kg per meter cube for MSA. MSA 20 mm and slump 80 mm. Okay, so it is the mixing water content 200. So now there is no such a reduction of the water content is not mentioned, because then fly ash, if we add the fly ash, then it is mentioned this water content is reduced. So actually in the IS code, based on the table, for additional slump, we increase the water content by 3%. However, we only and afterward we did reduce the water content by 15, as mentioned in the question, 15 kg per meter cube, 15 kg. However, in here there is no reduction will be will be based on the slump, because slump is already there. There is fixed slump. The tables are there based on the slump. We are getting this water content. So there is no such case of additional slump as mentioned in the IS code. And now we can directly so new water content after reduction 200 minus 15 kg per meter cube, so it is around 5, yes, okay, 185 kg per meter cube. Okay, 185 kg per meter cube is a water content. Now here in the ACI method we can calculate the air content for the non air intent and non air intent concrete. Considering this is as non air intent concrete, so air content air content for non air intent concrete, because we are not supplying additional air inside air intent concrete. Air intent concrete, non-air concrete, actually it is based on the maximum size of the aggregate. It is around 2 for 20 millimeter. It is, if you see the chart, it is coming on 2%. For MSA 20 millimeter, say 20 millimeter, okay, it is reduction is 2, okay, 2% the volume reduction, sorry, 2% of the volume of the total mix. Okay, so it is 2%. Okay, this is air content. Is there. Now we will go for the this water cement ratio, because in the IS method, because all information are already shared, so we don't have to go for a water cement ratio, because in the water cement ratio in the IS method, we water cement ratio is based on the experience, and it is based on the, if from experience it is not mentioned, the information is not shared, then we will go for the exposure condition, and based on the exposure condition we will fixing our water cement ratio. And water content will have already based on the maximum size of aggregate, we are already having our water content, and from the water cement ratio already water content we know, we can easily find out the cement content. So now now the thing is this fly ash content, yes, and now water cement ratio. So here the water cement is not there, water cement plus kf is coming, water plus the um, c plus kf means c dash is there. So cement so water new water is already there, water cement ratio. What is the water cement ratio? Okay. Yes. Actually, for non-air-rendered concrete and air-rendered concrete, both tables are there. For the air-rendered concrete, we have to interpolate. Actually, I have to again write it there. So, actually, this table are based on the cylindrical strength. And in cylindrical strength, the whatever values they are showing in the table, these are all are more likely to our mean strength. So mean strength is already provided here in the 35. So it's between 25 to 40. So for 40 for target, the means target mean strength for 40, the table say 40 MPa. This table are already mentioned in our previous class. I can, if you have your notes, you can check these values. So for non-air entrained concrete, non-air entrained concrete, non-air entrained concrete. So it is water cement ratio, water cement plus kf ratio is 0.42. Now for target mentioned 25 MPa, water cement ratio 0.61. Okay. Non-air. So our target mean strength is 35. Okay, MP. So so this volume fraction, this water cement ratio will get increased from 0.42 plus 0.61 minus 0.42 by 40 minus 20. This is simple interpolation, linear interpolation. There is no big deal. Okay, 40 minus 35. 0.61 minus 0.42 by 40 minus 25. This there is 5 plus 0.42. It is coming on 0.483. Okay, this is water by cement plus kf, because here not only cement is there, this fly is also there. So we have already calculated the water, and we have already calculated the fly ash content and cement content. So what are the cement content, what is the cement content and fly ash content, we have already calculated from our previous calculation. Is water content, sorry, the cement content, new cement content is C new or C dash equal to 291.06 kg per meter cube, and fly ash content is 124.74 kg per meter cube. Okay. Yeah, so I think you have to calculate this thing, and now water content is there, right? So let's check whether it is matching with this or not. Yes. So from here it is cave is there, and water is already what is already there, 200 by 0.483. Sorry, the water content is there. Water content is there 185 by 0.483. So it is 383.02. This is water content. Okay. So this cement plus K. Okay. So actually this we have already have this cement and fly ash content. So 291.06 plus if I add a kf, so k is already there, k factor is 0.3 mentioned, so k into fly ash content, 291.06 plus k 0.3 into 124.74, okay, is 328, actually 328.482 is coming, okay. um, hmm. Actually based on the based on this formula, if I calculate c plus kf, it is coming around uh, uh, 291.06 plus k 0.3 into 124.74, it's coming around 328.482 kg per meter cube. However, here is 383 based on the chart. We are getting 383. However, with the formula, we are getting this thing. So you have to be careful about this methodology, because based on the methodology, it can differ. Otherwise, you can simply follow our first calculations, where you can easily find out the this fly ash content or all these things. So this is the thing. And yes, and also if and I think this formula, this f by c plus f is zero point 0.3, because 30% is added here, and c plus f equal to 1.1 c, because whenever we add fly ash, it increased, the volume get increased or weight get increased, c total volume. So from these two we will be easily getting the c plus f. So there is no need to calculate this water cement ratio or find it from the table if it's already there. Water is already there for control mix. If it is not there, then we can calculate. If it is there, then we can directly find out the water cement ratio from it. Okay, then after water cement ratio, we can what we can do. Uh, mm, yes. And now actually here the target mean strength already mentioned. If it is not mentioned, it is in the ACI method, then you have to follow the two formula, where the two formula is there for cylindrical stress. FC dash plus 1.34 is one formula, another formula is FC dash plus 2.33 standard into standard deviation minus 3.5 minimum acceptable strength plus 2.33 standard deviation. So maximum of the two gives the target average strength or mean strength. So however, here already they mentioned the 35 MPa, so we don't need to get worried. Okay, now for the fine aggregate cement content is there, and cement already we can calculate the cement content fine aggregate fly ash content. Now the dry rodent density, dry rodent density, actually the density actually they don't mention here what is the dry rodent density, because it is only applicable for the ACI method. Dry rodent is nothing but this is the density of the dry aggregate that is packed in a standardized manner, and it actually is rodded in a particular container, or rodded using a standardized methodology. Means whenever we compact the aggregate, it follows some rule. So we basically make it a 3-layer arrangement, and we shake it and we'll pack that aggregate, and then aggregate is the dry mass. Okay, so based on the dry mass, we are finding out the dry rodent density, and from the dry rodent density you can easily calculate this content, because of tables are there based on maximum size of the aggregate, coarse aggregate, and finest modulus, because finest modulus is not here. So and you can get the volume fraction of the fine aggregate, coarse aggregate. Okay, so and you can easily calculate the we can easily calculate the fine aggregate content. Okay, and coarse aggregate and fine aggregate content. Okay, given the specific gravity and all that. So this table where the finest modulus is mentioned, and based on the maximum size of aggregate, you'll be getting the Course aggregate volume fraction. So the volume fraction will be multiplied with your this dry rodent density, and you'll get the how much Course aggregate you have. Okay. So these are the way you can solve this problem. Now I think all the questions are covered here in the lecture. Because there is some little more ambiguity, still some ambiguity is there in the question, so I try to cover in both way, in both the method. So there are some differences in based on the methodology, and there's some more extra information here, so you should be very much careful while taking the information, so don't get messed up. Whatever information available, you have to utilize as much as possible so that you have the relevant answer. And so don't get worried about the information whenever there is some diversion also there, so you don't have to be diverted based on your the so many information. So whatever information you need, you just pick this information and calculate your on your own, and on your own IQ. Based on your IQ we can calculate this thing. So now I'll try to uh, show regarding this today's lecture. Actually this week 6 lecture, I have some point that I already noted down. Based on that, I will be giving some important points, if and you can remind that before your exam. Okay. So first is actually lecture 7. We have already discussed, and lecture 17 is already discussed in our previous while solving our previous previous weekly question. Now I can directly skip that lecture because we have already covered. Although it is not shared in the week 5 lecture, still we have managed to perform the answer, or to carry find out those answers that are in the week 5 assignment content. So it was very much fortunate that we got that as answer. Still there is no relevance of the weekly content, lecture content. Now I'll start from lecture 18 itself. So the uh, lecture 18 starts with the packing and rheology. Actually, the rheology is nothing but the study that which deals with, or by virtue of, or the study through which we'll find out the flowability of the concrete in plastic state. Okay. So actually this is called the rheology, flow behavior. Flow behavior. What is the flow behavior in the plastic state? That is called the rheology of the concrete. So in the fresh concrete, the rheology is such that in the it is in the moldability. We can mold that concrete, so it is in plastic. It should be in plastic state. Cohesion is there. Cohesion means between the paste and the aggregate. Cohesion should be there, so there is no bleeding and segregation. After vibration also, after we placing it, we have to vibrate it, and there should be no segregation. We have to design in such a way, so it should be cohesive mix. Okay. So yes, I have written some points for your own um, comfortability. You can remember this point. I think it will benefit you in your exam. So in the lecture 18, the first, the concrete is a particulate system bonded together, and the fresh state it is a weight state, weight density we can say. In fresh state it is a weight and aggregate system is there, and actually the with the aggregate and the weight paste, it makes the concrete structure. So so largest coarse aggregate particle are packed together with interstitial voids, because whenever the coarse aggregate is there, there is some interstitial space should be there, and the interstitial space either will be filled by water or it will be filled by the air. So with the control mix or with the mix design, we have to make it as less as possible, the void as less as possible, and we have to and whenever there is a consistency, that we will be going after the consistency, then this void should be breaked, or this void should we have to make it in such a way that we have to design the concrete in such a way, or proportion it the constituent in such a way that the these voids actually, the if you see the voids in microscopic view, they are in chain like system. So with the addition of this or proportioning, with proper proportioning, we can break the chain, and we can make this air or the void in bubble shape. Air content is bubble, then not in a tube type section. So it should not be in a chain, it should be in bubble form. So when that condition reached, then we can say it is a consistent or consistency. The cement has achieved consistency, because so the main purpose of the consistency is to break the air chain into bubbles, air bubbles. Okay, so this is the interstitial space, and this voids will fill with smaller particles. Okay, so actually I have to write this some for your own understanding. My health is not good today. So these are the particles. This is the coarse aggregate example. Coarse aggregate, right? This larger particle, okay. However, this particles, the space. This is the interstitial space. These are all the interstitial. Sorry. Here. And these are the interstitial spaces. These are all the interstitial spaces, and these interstitial spaces can be filled with the smaller aggregate. Okay. Now from the smaller aggregate, the void get reduced. However, the still voids are there. So yes, this interstitial the interstitial position can be again filled by smaller particle. This is fine aggregate. Sorry, it's fine aggregate. So this is the fine aggregate particle. So fine aggregate particle is can filled here. Fine aggregate particle you can fill here, and between the fine aggregate particle there's also some space available, and that space can be filled with the paste. The paste is nothing but cement or fly ash, cementous material plus water. With this paste have, so this paste is very fine, and this fills all the voids among the fine aggregate. So our mix should be designed in such a way so there is a minimum void can exist. So we design in this way. So and packing. So it should be a better packed. Unless until it is better packed, this and the concrete doesn't get the good strength and high strength. So the further voids in the further voids can be filled with the paste. So we have already mentioned in the our previous classes, and we already discussed regarding the this packing density, void ratio curves, and based on the void ratio curve, how the packing density behaves. So these two curves are there. So I think I have to write again this. If you are using the binary system, because two aggregate you are using, one aggregate A and the aggregate B. So here this is the volume fraction. Volume fraction is there. Volume fraction. Here void ratio is there. So when there's a E maximum, this is a A is B aggregate here. So here this A aggregate is volume fraction is total volume fraction, B 0. Here A is 0, B1 is 0. Okay. So maximum. Okay. So if the graph follows this way, and it is EA and EB, and when there is some there's a smooth transition, actually it is mathematically can be calculated. The smooth transition is there, so it will be at this volume fraction we can get the maximum, the minimum void content at this volume fraction. So volume fraction of both this A and B. In corresponding to this graph, if we draw the packing density, this packing density is here and volume fraction is here, A, B there, okay, and it's just opposite, okay. So at which point the volume fraction is, at which volume fraction, optimal volume fraction, the void ratio is minimum. So at the same volume fraction, the packing density is much more. So actually we can calculate this volume fraction and find out this packing density. Okay. So the theoretical equations are there based on this find out this packing density. One of the theory is led by D. Lard. Okay. So actually from simple experiment you can do this. It is a empirical formula. From the simpler experiment you can find out this 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 packing density. Which is a packed aggregate mixture and in defined proportion. So it should be the mass proportion, because if it is a volume proportion, then it is very much difficult to maintain the volume, because in the volume some in the particular one container has one particular volume, and whenever you are batching some aggregate one volume, so and 1% and just shake the containers good better way, so the aggregate get packed and they get compacted. However, another person, whenever they shake it, so the aggregate doesn't get packed, so it becomes a loosened state. So and sometimes you have to travel it above the top. In the previous cases it doesn't happen, so will be getting in different masses for aggregate. So in this for same volume, so the volume proportion is much difficult to control. However, the mass proportion you can easily control, because we have to weight the mass how much it is. So it is easily it is based it is on our reach that we can control this mass proportion. So this density is formula is a dp. dp is there. dp is the w is the weight of aggregate by gravity, specific gravity of aggregate by total volume overall. So actually this one is this is a bulk volume. Okay, however we can segregate with the for each aggregate. So the dp can be nothing but the summation of this all the densities. So, course aggregate 1. So course aggregate 1 has w1, it has the g1 specific gravity. Course aggregate w2, it has g2 capacity, and now is total volume is there. Okay, so you can easily identify this. So, and based on the volume fraction, we can do a trial of several trial and find out the best packing density where this is become maximum. So the curve will be coming like this. So at this point, this at this volume fraction, this packing density will be maximum. Okay, so it is very unique. Okay, so one volume fraction you get, you just divide from 1, you will get the second volume packet. Because if you are just dealing with the two binary system or binary component, two aggregate is there in the system. So for a particular case, if you get the one volume fraction, you just minus it from 1 and you will get the other volume fraction. So this way it can be calculated. So actually now let's choose the best proportion which gives the maximum proportion. Means this volume fraction. See, is 1 is 2 is there, aggregate is there. So is 1 you find out by trial mix, doing trialing. You found out that the course aggregate is 1 is the 60%, and if it is 2 is 40%, then it gives the maximum highest packing density. So it is the best proportion, and you get the M20 M12 for the mix, and for the for aggregate maximum size of aggregate 20, and you can do it by trial 20 or 10 and you will find out the packing density. This way you can do the this find out the packing density based on the experience. Now packing density is done. So you got the packing density, maximum packing density, and based on the packing density you will get the minimum void content. So minimum void content, so it is nothing but yes, packing density is there. Yes, so it is 1 minus, so void, the void will be, so void will be 1 minus dp, sorry, 1 minus dp max. Actually there is also effect, this density. If you get the density, if you get the void, it will be much less. However, the void will be much more because of the wall effect and loosening effect. The wall effect, you already know that, already we discussed in our previous class, that wall effect due to first of all I want to say that loosening effect, because whenever you add fine particle in the or paste inside the aggregate system, it will disperse the aggregate system. And also due to the wall effect, uh, at the boundary, this fine aggregate arrangement get disturbed. So it also the dispersion also takes place. So actually it find out this 3 to 10% of dispersion take place in the cement paste or aggregate system due to the wall effect and the loosening effect. So it will be 1 point, sorry, it will be 1.1. I have to the white content will be much more 10%. We can take the 10% and it's 1.1. So so actually the more the packing density is less the paste content, less the paste content. So okay, so so the paste content should account this packing density and also the wall and bruising effect. So fresh concrete contains the 30% voids and and sometimes it confirms the shape of the mold also. So in the fresh concrete 30% voids is there, and actually in fresh concrete it is in as because it is in plastic state, it doesn't have a solid structure. Okay, after hardening it gets a structure, hardened structure. While compacted by the vibration, fresh concrete must yield easily to deform under shear and maximum shears, and however the maximum cohesiveness should be there. So the um, so, yes. Okay. Actually, yes. So when vibrated, so it should yield easily to deform. So when there is a shear deformation, it should follow the shear deformation and flow like a, not fluid, like a plasticity. Should have the plasticity. So now if we consider it is a fluid, so flow of fluid takes place against the frictional resistance offered due to immediate next layer because of the boundary layer theorem also there, and it whenever there is a viscosity, so one layer also tries to oppose the movement of another layer above it. So so this paste has also the viscosity. So in yes, the concrete not in solid in the fresh state as it doesn't have the definite shape, and before it becomes the solid it should be in plastic state. Okay, one have to apply the stress and it will start to deform. When the plastic state means one have to apply, there will be without application of load there will be no deformation of plastic state. Whenever we apply some load and based on the load direction, the material will deform. So this is called the plastic state. So subject okay, so the cohesion should be such a way that there should be no segregation or bleeding. So bleeding segregation means say aggregate gets separated out or water gets separated out. So this segregation, we test the segregation by conducting the tensile strength of the concrete. Okay, this cohesiveness, the cohesiveness we check the cohesiveness using the tensile strength of the concrete. If the tensile strength is very much low, then aggregate will separate out. So in the solid state the solid state the this actually I will mention this formula. For solid state it is directly proportional to tau is directly proportional to shear stress is directly proportional to shear strain. Okay, so however for the liquid it continuously deforms whenever it does not matter the the shear stress is small or large. Okay, it will continuously deform. And for the liquid it is solid. For the liquid it is mu dy by d gamma by dt. Okay, actually it is the shear strain rate. Mu is the viscosity and this is the shear strain rate. Okay, shear strain rate, shear strain rate, shear strain rate or velocity gradient, velocity gradient, velocity gradient, gradient. There is a Newtonian fluid, so Newtonian fluid is like likely, so likely that yeah, this tau is equal to mu dv by dy. Okay, so velocity gradient is there, and its velocity gradient is nothing but so use dx by dt. This dv is velocity, dx by dt by dy. So it is nothing but uh, sorry, I'm mistaking it. Yes, so it is, you can write say dv equal to d yes, v equal to x by t. X by t is there, dy. So dx by dt, dx by dy by dt. Okay, so it is nothing but dx by dy is nothing but shear strain. So it is the d gamma by dt. So it is a shear strain. So actually it follows the Newton's law. So in the plastic state, the above would happen um, after applying some certain stress, certain load is applied. This deformation, this relation will start to follow after we apply some certain load in plastic state. Okay, so actually in the plastic state, so we have to make that amount, so that load, whenever we reach that load intensity, then it will flow like a Newtonian fluid. Okay, so it flow like a Newtonian fluid, or it will have the velocity gradient. So if you draw the graph, actually in previous class I have also draw the graph. So this is like this portion is there, then it started this. Okay, and this is the Newton, this is the Newton. Okay, Newtonian. This is Bingham fluid, Bingham. So actually this here to here, it is a solid state, so there is no deformation. After that, this tau is there. After particular shear deformation and rate of shear rate of shear deformation, so after a particular loading rate, it will try to behave like a fluid flow will be there. So there is a certain point 1 2 is there, 1 2 2 to 3 3 to 4, and in 3 to 4 it will completely behave like a fluid. So it is like a fluid. However, in 0 to 1, it will be like a solid, there will be no flow. However, in the 1 to 2 there will be little flow. However, there is sticking nature. 2 to 3 the flow is going to be mobilized, and 3 to 4 is fluid flow is there and follow a gradient. Okay, so if it is there, the gradient is there, it is the mu. Okay, and this mu is the nothing but the shear viscosity. This is mu, and this is called the yield shear strength. This is yield shear strength. Okay, so that is the thing. So in the concrete, which is the plastic state, when the concrete at plastic state, concrete at plastic state behaves like Bingham, because at the plastic state it have to we have to apply some load, then it will deform. So it follows the Bingham theory. Okay, so addition of water increases the shear strain, increases the addition of water reducing agents. Also some increases the plastic viscosity, some decrease the plastic viscosity, and reduce down the yield stress also. So addition of water increases the shear strain. So you have to, there are some points I discuss. Okay, so less water, if you add less water increases the, if water content is less, then is the viscosity is getting increased. Okay, and increase the tau also. Okay, so increase the tau. The more paste is there, more paste is there, more paste is there, then increase the yield shear stress, increase the yield shear stress, the tau naught will get increased, and okay, and increase the shear stress, okay, yes, increase, and now lower paste, nothing much is paste lower, then viscosity will get reduced, viscosity will get reduced, yield shear strength will increase. I think it is will decrease. Yes, it will decrease. Shear strength will decrease. Its shear strength will decrease, and its yield shear stress uh, lower paste, lower paste, yield shear stress will increase. Okay. Uh, yeah. Uh, yes, for the P get increased, mu also get increased. Yes, actually, if you use the more cement paste, so more cement paste, the viscosity will get increased. Yes, it will give the cohesion. However, the shear strength will get reduced. So it will have the adverse effect on the shear strength. So resistance, in terms of resistance, it may be not the right choice. Okay, so now the viscosity, there's also some formula was also there, and it is not that much descriptive. However, you have to can remind this for your own exam purpose. Okay, sorry. Okay, now this paste, or yeah, this paste form the matrix. This paste means this cement plus water form the matrix, and whenever the in the matrix the aggregate system are there, and it lubricate this aggregate system, and we can find out there's a dispersion of 3 to 10%, and there's also the effect of wall effect and loosening effect also coming in picture because of this lubrication. Okay, so this is the degree of dispersion. Degree of dispersion is 3 to 10%. Okay, remind it. Now decreasing the volume of the matrix reduces the dispersion. Volume matrix is like the paste matrix is the paste. Okay, so decreasing the volume matrix reduces the dispersion. Dispersion will get reduced and increases the particle interference. It's obvious that whenever you are decreasing the volume of the matrix, so particles will come closer to each other, and interference will take place, and stiffness will concrete will get increased. However, there is some limit of it. So normal consistency means 32 for the cement paste. For cement paste is 32%, and for the flowable concrete it is 37 or 38%. So self concrete is also more the normal consistency with the water content. So below a level, lowering the volume of the matrix would result harsh and segregate would result harsh concrete, and make the concrete in make the concrete segregate. Okay, so there should be some level at which you have to lower the volume of the matrix, because too much lowering will increase the harshness, and also it also cause the segregation. Okay, now increase the matrix volume. Increase in matrix volume improves the concrete consistency. Yes, the matrix volume is to get increased means the water content also get increased. So the matrix should have the adequate consistency. Yes, low water cement ratio matrix may cause the dispersion, but cannot hold the aggregate together. Yes, whenever the low water cement ratio in the matrix, the aggregate can't be hold together, because at certain stage, the if you lower, if you can't keep on lowering that matrix volume, as because you have to bind all the aggregate together, so stiffness will also get reduced, and the aggregate also gets separated. So normal strength of the concrete have the water cement ratio more than the normal consistency. So at 26% to 33%. So now the space content shall be adequate not only to fill the voids in the aggregate but also more than that, because for proper dispersion. Okay, so paste content should it's so paste content should be adequate to fill the void, and it should be taken care of. It should not disperse the other aggregate. Okay. So for economy and other factors, the paste content in the normal concrete ranges from 28 to 32%. Okay. Now there are several formulas which actually helps us to find out the aggregate content. Okay, so aggregate content is if you are using two or three a mixture of two or three type of aggregate, what are the content? Okay, actually the formula I can write is there. I will try to find quickly. Right, this water content is the water by 1000. This is all the volume, right? So this cement is there, C by 3150, and so 1 minus dp max means this packing is into 1.1. Okay, now one formula is there. Then from the another formula is this water cement ratio or water cement plus kf is there equal to water cement durability consideration, durability. Okay, and third equation is this, the aggregate is the two or three aggregates are there. So aggregate course aggregate 1, this course aggregate volume fraction, course aggregate 1 plus course aggregate 2, one volume fraction is there. Actually this volume fraction is weight mass volume fraction, mass fraction, not volume fraction, mass fraction is here. Now 4 is the if two aggregates are there, and we are finding this WC1 WC is fine aggregate also there. C2 is fine aggregate. Okay, F2, and lastly we will get WC1 by GC1. I have already told you in the previous back to some previous few hours back, this and the way you can find out this density and also this packing density. Okay, so Ca2 by GCA2 plus WFA by GFA. Okay, 1000 into dp max packing density. Okay, so these are all the volumes, and okay. So with these three formula we can easily find out the WCA1, WCA2 and final aggregate, and these are the formulas we can easily find that water or cement material. This is coarse aggregate type 1, coarse aggregate type 2, and fine aggregate will this three equation will guide us to find that, and these two equation will give us the water and cement content. Okay. Now the mixed proportion obtained would have the least flow properties given the water content. To increase the slump, add maximum possible dosage of compatible water reducing agent determined by mini slump test. Okay, so actually in mini slump test, what we do is the this thing is there, this column is there, and this is there, 38 mm is there. Okay, and this is the 50 mm, this is mini slump cone 50 mm, and this is the 19 mm. Okay, and we just to check the flowability. Okay, we just put the inside the we put the concrete inside and just lift it up, how it's getting spread, and we can find out. So the superplasticizer, actually we are finding out the flowability if we add different type of superplasticizer, and the also graphs are there. This is the graphs are there. So these are this superplasticizer 1 2 3. Okay, so, okay, superplasticizer 3. So at some point at some point. Actually this graph is like a flow. This here flow is there and dosage is there. Okay, dosage is there. A particular one dosage it gives the maximum amount. So the best choice of plasticizer is that the best plasticizer gives maximum flow at minimum dosage. Okay, maximum flow at minimum dosage. So now these are the way we can find out the flowability. Now in the lectures line covers batching and mixing, because mixing is also very important, and batching is also, the batching is nothing but the process of measurement. Okay, how we measure the specified quantities of cement, aggregate, water and mixture. Okay, so batching is, volumetric batching is there, weight batching is there. Volumetric batching is not desirable because it is very much difficult to control the volume. However, the weight batching in the Indian scenario image, it is largely adapted. There's also some plant type with cyclic, continuous, and manual also there. And for considering the accuracy of the weight batching, IS 456 recommend plus minus 2% for the quality concrete, and plus minus 3% for quality of the aggregate, quantity of the aggregate, water and mixture. And some tolerance also there. The tolerance also mentioned for cement and other cementous material, plus minus 1. Waters, actually tolerance is there, tolerances is there. Cement and other cementous materials, plus minus 1% is there. Water by volume or weight, it is plus minus 1%. Aggregate percentage is plus minus 2. Okay, admixture it is plus minus 3. Okay, now this tolerance can be calculated this way: 0.3 minus scale capacity by weight tolerance. Okay, this is a tolerance. Okay, tolerance. So actually, if we have the the weighing system has the 1000 kg capacity, so it should be 1000 capacity. And now tolerance can be calculated based on the cement material, it is 1. So based on the tolerance type, we can calculate the total overall tolerance for that particular plant uh, the material. Okay, so uniform concrete exhibits less variation, because the variation is, tolerance means the variation. Whenever we are finding to obtaining to 37 megapascal concrete, so the variation should be not should be minimum. So if it is, the variation is plus minus 2, means we are getting 35 or 39, the variation is in range. And at another batching we are getting variations of 34 plus minus 3, plus minus 5, 32 to 42, then variation is much more. So the uniformity is not there. So so that variation, this plus minus 2 variation is much less. That is also desirable, because based on our criteria, what is the desirable strength of concrete. So variation depends on the variation in properties. Example, if you keep on increasing the cement content, water also increase, and errors in cement and water measurement is also come, and it also vary the strength in batch to batch. Okay, the quality means this less variation. The quality means less variation. Proper batching ensures the better quality. Okay, thorough mixing is essential for production of uniform concrete, okay, uniform and quality concrete. And equipments and methods should be capable of effectively mixing the concrete material containing the largest specified aggregate to produce the uniform mixture of the lowest slump and practical for the work. Lowest slump that available for the practical, that will be sufficient, or that will be required for the particular work. So mixtures, there's a different types of mixtures. Cyclic batch mixture are there, gravity mixtures are there, the counterflow mixtures are there. So and now the mixing time, consider the mixing time. The mixing time should be short, usually short, and depends on slope, and useful in the low slump pavement concrete. actually low slump pavement concrete, this mixing time should be less. So now the mixing should be such a way, yes, and for the IS code it is mentioned that 1 minute for 75 meter cube concrete, okay, 0.75 meter cube concrete for addition. Now 2.5 minutes required for each addition of 2.25 meter cube of concrete. Okay, so I'll quickly write this here. This 1 minute for 1 minute for 0.775 meter cube concrete, and plus 25 minutes will be added. It will be added with 1 minute for each, for additional 0.25 meter cube capacity. So uniformity states that tests of the sample of fresh concrete collected from the mixture at different stages of the discharge, okay, from the batching plant. So actually from the batching plant, whenever the hose is there and the discharge is coming, and you have to take when the first discharge is coming, the first this this IS code, IS 456 mentioned 2 minute mixing time. After 2 minute mixing time, the discharge is coming, and 2 minute. Okay, so 2 minute take the first 15% of the 2 minutes, means 120 seconds. Okay, so that's 15%, 19 seconds, and last 19 seconds, because the variations can come. So we use like that way. First 15 19 second you collected the samples, you find out the concrete strength and all the other properties, and last 15 minutes 19 second you collected the samples and find out the strength and also the aggregate content by charging the jet water, and find out the aggregate content how much. So you can find the uniformity, whether the uniformity is maintained or not. So the thing is, there is some chart in this sorry, this chart is there. Here is like that. So this thing is there. Okay, so actually this is the mixing time. Mixing time is there. This is the wet mixing time. Okay, wet mixing. This is the dry mixing, and this is the solid component content. So here this is we charge it, and we add some water, and after and here we also add some water in this section. This is the loading period, and okay, loading period, and after here we are not adding anything. So this is the pure mixing time. Okay, and this is the discharge period. Okay, this period. Now there is little difference with the IS 4925 168, because they told that mixing time for each batch of the material except full amount of water, period of all mixing water shall be introduced before 1/4 mixing time elapsed shall be 1.5 for 1.5 minute 1.5 minute for 2 meter cube concrete, 2 meter cube concrete, and 2 minute for 3 meter cube concrete, 2.5 minute for 4 meter cube concrete. So these are the guidelines based on the IS 4925-1968. Okay, so increasing the mixing time is resulting in more uniform distribution of hydrated products, resulting higher compressive strength may result. However, prolonging the distribution, because if you keep on mixing, if you keep on extending the mixing process, then with the round or this rolling or some action, because there is some tilting device also there, because the machine where the materials get mixed up, due to the crushing and also the abrasion, the aggregate also gets crushed up and the fine aggregate become more, and it may not give you the desired strength. So prolonged mixing process may not increase the strength proportionality and may result in a decrease in some cases. So you have to be careful. So and mixing time also, yes, excessive mixing leads to the segregation of the for the linear concrete, means the concrete is that don't designed in a specialized way or a desired way. So for the lean concrete, it will segregate. So for the purpose of this mixing, the tilting type mixture is not desired. Tilting type mixture is not desired, and however the bottom discharge mixture is desired. Okay, so bottom mixtures is desired, and in the, such in the, whenever there is a tilting type, the aggregate has a tendency to come out fast, then later the paste will come. Okay, however in the bottom mixture, this problem doesn't exist. Okay, so this way it can happen. So so it this much, and I think we can discuss few questions regarding the that I promised. Okay. Actually we now already we have covered this 31. Okay, so 31 till 31 we have already covered. Yes. Okay, 31 we already covered. So okay, so yes, the 31 is the as per 7320-1974, the internal dimension of the mold of the slump test. It is not a mini slump. Okay, normal slump test. Bottom die is 200 mm. Bottom die is 200 mm. Okay, this is the bottom die. This is the bottom dia. Bottom dia 200 mm. Top dia is 100 mm. Okay, top dia is 100 mm. Actually this is the slump cone. Okay, and this is the top dia, this is the bottom dia, this is the height. Okay, this height is 300, height is 300, height is 300, top bottom is 200, top is 100. Okay, so it's C with this answer is now addition of the calcium chloride in the concrete results in what? Addition of concrete accelerator. This is an accelerator. Accelerator means setting time and grade decrease. Setting time grade decrease. Decrease the setting time. It should be B. Okay, it should be B. So concrete mix design is 10262. This FAB 33 102. Yes, yes, 10262. This is the right answer. Now IS 452-2000, the organic content of the water used for making concrete should not be more than what? More than is 34. Actually IS 456 mentioned the organic content. If you check it, this organic content, I am just writing here. Okay, organic content, organic, actually is organic content is 200 milligram per liter, 200 mg per L. Inorganic content, inorganic, this is 3000 unit. Sulfates is 400, and chlorides is 2000, or suspended matter, it is around 2000. Okay, so for organic it is 200 200. Okay, so option A. Okay, the grade of the M20 concrete meets the characteristic of the concrete compressive strength of 15 centimeter cube. After 28 it should not be less than the 20. So it is the 20 is okay, it is mm, grade of concrete means yes, 15 days. Yes, uh, is 20. So maximum admissible water cement ratio for the mild exposure condition. Maximum water representation, I think, point 0.4. We have already discussed today what is the maximum water cement ratio. Maximum admissible water cement ratio for the yes, mild environment condition. Maximum water cement ratio is the 0.55 or 0.6. So 0.55 is the reinforced concrete. Is the reinforced concrete. 0.6 is the mild plain concrete. Okay, point plain concrete. So it is option A. 5.36. Sorry, what is this? I think for the mild condition, right? They are saying the maximum admissible water cement ratio for the mild exposure condition. Yes, mild exposure condition it is 0.6, right? A 0.55. Yes, mild exposure condition it is 0.55. Yes, I think they have written some wrong. Yes, no, it is A only. So air entrainment in concrete increases the workability. Yes, it should be the workability, but not the decreases the strength. Okay, doesn't decrease the strength, workability. Okay, now which of the following acts as a retarder in the concrete? So calcium lignosulfate, calcium chloride, calcium chloride is not there. Alumina powder, calcium lignosulfate. Calcium lignosulfate is the most probable answer. So actually, retarder is the few retarder is the gypsum is there. Gypsum flash shedding property is there. Reduce the flash shedding property. Sugar, so these are the retarder. Okay, sugar and calcium reducer. So this is the question. The identify the wrong statement. The bulking of the sand can go up to 40%. Bulking of the sand is maximum at 4.6 moisture content. 4.6% moisture content. Bulking of sand is considered in the wave batching. Bulking of sand content, the wave batching is not possible. So bulking of the sand occurs due to pre-moisture film formation over the sand grain. Okay, these three are right because these three are relevant. However, the bulking is considered in weight batching. Bulking is only the volume batching thing is there. Whenever the volume batching bulking comes in pictures, let's see, 5 to 39. Okay, so it is C. Yes, it is C. This is most answer is C. 39. Okay. Yeah, so see that the coarse sand has the finest modulus in the range of I think 2.4 to 2.6 to 2.9. Okay, uh, 40. Fine is 2.2. Actually, the fine is 2.2 to 2.6. Medium is 2.6 to 2.9. Coarse is coarse fine aggregate is 2.9 to 3.2. I think the coarse fine aggregate finite model 2.9 to 3.2. Okay, so it's around I think yes, D. The top dia bottom dia of the cylinder slump test is already discussed. Separation of the coarse aggregate from the transportation is the segregation. Okay, water cement ratio is a measure of water cement per cubic meter by volume, weight by weight. Is weight by weight? Yes, already is weight by weight. So water cement ratio is nothing but the ratio of the weight of the water and weight of the concrete in the concrete mix, and it is the okay. So it is a weight by weight. So it is like B. Okay, so to prevent segregation, maximum height for placing concrete. So we can't place the concrete at certain height. So that height should be maintained. So we can't throw the concrete. we can't throw beyond that height, otherwise it will get segregated. So what is the actually IS 456 2000, it should not be more than maximum permissible free fall of the concrete. This is free fall. Maximum height means free fall. Okay, free fall of the concrete is 1.5 meter. 1.5 meter means 1. So now we just cover a few questions. We start from 45, from question number 45 in the next class. Thanks for joining. Okay, I'm unsharing my screen. Unsharing my screen. Okay, okay, I'm sharing my screen. So thank you guys for attending. Thank you. Good evening.
Thank you, sir. Thank you.
Okay.
Thank you, sir.